Okay, we're ready to restart. A few words about security. Security is not the focus of this course, but we will try to mention at least the security implications and the basic solutions of what we're doing. As we've seen and described the MAC addresses and the MAC layer in general, everything is sent in the clear. If I create a packet, I put a MAC destination address, and then by the virtue of this MAC destination address, it will go to a certain destination. Of course, this is easy to attack if we do nothing else. We can do the number of attacks. For example, eavesdropping. Eavesdropping means I can capture someone else's traffic. That's what we do when we do Wireshark, when we put our adapter in promiscuous mode. Free riding means inserting yourself into a network. You visit a place somewhere, you go to a university in the States, you find an empty office, you get into the office and you connect to the Ethernet. If the switches are, like I said, this should work. And worse, of course, impersonation would be the fact of forging someone else's MAC address, perhaps IP address as well, in order to get data that is not for you. There are solutions to that, of course, that collectively we can call them MACsec. So security exists at different layers. Now we're talking of layer 2 security. Layer 2 security is about controlling primarily the access to the network. MACsec is deployed typically on a wireless network. On a wired network, there are some proposals, but most of the time, security is not really implemented there. But at the wireless network, certainly it is practically always done with different set of functions. The simplest function is access control. Access control means you cannot access this network unless you show some credentials. The EPFL Wi-Fi network is of that kind. You cannot access this network if you don't give your Gaspar username and password. So this is a form of access control. This is also typically what you have in the Wi-Fi network we have in INF019 or your Wi-Fi network at home, where you need somehow to know a secret key or a password or some kind of secret that is associated with the SSID. In the case of the network we set up, it's not very secret, but at home probably yours is more secret. So this provides guarantee, strong or weak, that only people who know the secret can access the network. That's the very minimal set of functions. Enterprise networks typically use also encryption and authentication. Authentication of the MAC frame. So that means every MAC layer packet is encapsulated with an authentication header that serves as a signature for this packet. So the packet is signed and also numbered. So signed by a key that you obtain during the access control phase. So this is typically done for the Wi-Fi network of EPFL. So when you connect to the base station, not only the base station will check who you are, but you also agree on a secret key that is used for signing all the packets of the session. And then all the packets that come from you are signed, and if they are not correctly signed, the packets are discarded. So the signature is used to verify just the authentication. Typically, it's combined with encryption, which also makes sure that anybody who can sniff the packet will simply see a random string of bits. In particular, all the MAC layer data is encrypted. The MAC destination address and the MAC source address are not encrypted because we need them for the operation of the MAC layer. But anything else than that is encrypted, so that if somebody manages to sniff the packet, to copy the packet by forwarding them to a forged MAC address, we'll simply have binary random data. If the encryption is strong enough, that will make it unusable. In particular, you will not see which IP header there is. You will not even see whether it's an IPv4 or an IPv6 packet. As I mentioned, typically in enterprise networks, the whole gamut here is deployed, and in smaller private networks, typically you don't have the authentication and encryption, which means in particular when you access a Wi-Fi access point somewhere, and if you have a data flow that is not encrypted at the application layer, then people can see all the data that you're sending. So typically, if you access an access point, a Wi-Fi public access point, you should use some solutions for encryption and authentication at higher layer. One of them is virtual private networking that we'll discuss a bit later. Another one is application layer encryption. The consequence of this is this quiz now. Which I let you discover. So Bart is a legitimate EPFL student and wants to give access to his daughter Lisa. And because he took the course TCP-IP, he knows how to configure his PC as a bridge. And therefore would like to give access to Lisa. Will it work or not, or in some cases? I close in 5 seconds. And the correct answer is it won't work. It will not work because at EPFL there is not just access control, but also encryption and authentication. So all the packets that are issued by Lisa will be forwarded by this, but the content of the data will not be signed by Lisa because the adapter of Lisa doesn't know the secret agreement that was done between the adapter here and this guy here. So the data will not be encrypted. The bridge will simply forward them. And this Wi-Fi base station will not see a correct authentication header, or will see no authentication header, and will simply dump them. So it won't work. In some sense, MACsec is able to guarantee security of the access, to control the access to the network. Yes?
Because, as you said, if it's a bridge in the middle, then the source destination doesn't change. So the EPFL network would know that's a not unregistered network.
Exactly, yeah, yes.
So it wouldn't even pass the access control.
So it will not pass the access control, correct. Yes. So let's try something else. I close in 5 seconds. The majority is B, and probably it's correct. We would need to try. You never know in reality if it works. But probably the correct answer is yes. It would work. I mean, the mental model of a NAT is, if you remember, for the outside, everything is as if everything was inside the NAT. So everything will appear to the rest of the world as if you had, Lisa was simply a different process in the same PC. The NAT acts by recreating IP packets. So when Lisa sends an IP packet to someone else, the NAT will forge the IP headers and also manipulate the TCP ports as if this was sent by a process inside this machine. Then when it's passed to the Ethernet adapter, all the correct encryption, authentication, everything will be correct, and therefore it will work. Yes?
What about the payload, the IP payload? Would it change it, the NAT?
The NAT will not change the IP payload, but it will encrypt it. It will encrypt, the NAT will receive the payload, the Ethernet adapter will encrypt the payload, and the Wi-Fi base station will be happy, it's correctly encrypted and signed, It comes from this machine. So as soon as you put a NAT, everything is as if this would simply be a process inside the NAT. Yes?
Here the NAT is only at the layer 2.
The question is, here the NAT is working at layer 2. No, a NAT is never working at layer 2. A NAT is a hack that is above layer 3, in fact. So it manipulates the layer 3 header. So the NAT is, of course, never at layer 2. Voilà, that's all for this chapter. Now we move on to the next topic, which is not following the hierarchy of layers, but is following the needs of the labs. So the next topic is the transport layer. The transport layer will be the topic of the next lab, or more exactly, the use of the transport layer by programmers will be the topic of the next lab. We have seen already what is the goal of the transport layer. The goal of the transport layer is to make the network services available to programmers. And in principle, as usual in TCP-IP, it's only in principle. In principle, it exists only in the end systems. And we have seen that there are two flavors, UDP and TCP. There are zillions of different so-called transport protocols, like STCP and all kinds of variants, but they are not really transport layer protocols. So you can implement on top of UDP your own way of doing a programming interface that provides reliability, but it will be on top of UDP. So strictly speaking, what the internet offers today is only UDP and TCP. We will see in the lab things like WebSockets or constructions that are at the application layer above UDP or above a combination of UDP and TCP that provide better programming interfaces. This we will see in the lab. Right now we will discuss mainly TCP, but before a few words on UDP. UDP uses port numbers. We've seen them in the context of NATs, for example. So here, a quick recall. UDP has a header, even though it's doing practically nothing. So UDP is a mechanism to send one message from one process on one machine to another process on another machine. So when you send this, you need to send to a given IP address. This function is given by the IP header. But you also need to identify to which process you're sending the packet, because most machines have multiple processes. So the processes are reachable via numbers that are called the ports. There are well-defined ports, the lower number ports below 1024, that are, for example, 53 is for DNS. So a large number of ports, so those small number of ports are pre-reserved and defined. So number 53 means there is a process that's listening to this port, and it should be, in principle, a DNS server. In principle, of course, there is no physical mechanism to prevent you from making a web server, for example, listening to port 53. You can do that if you have enough privileges to break a number of things in the operating system, but in principle, you don't do it. You also have a source port number, because when, for example, your DNS resolver here sends a query to a DNS server, the DNS server will need to respond, and the response will be sent to a given port number, which is now a transient port number, not a permanent one. It's a port number that's allocated to this process on the fly by the operating system when the process starts communicating. And those port numbers are in the UDP header. So UDP header contains source port number and destination port number, 16 bits for each of those. And the data. It also contains the message length and a small checksum, which is a weak error detection code based on modulo arithmetic that can be used to detect at least some bit errors. UDP is message-oriented. That's an almost obvious thing. It simply means that if you send a UDP packet, you will receive this UDP packet unless it's lost. You will not receive half of it. or you will not receive this packet together with the second message that was sent before. They will not be glued together or split into two. Which means that as a programmer, when you are connected to a UDP socket and you want to read data, you do a read call and you say, read something. If I get one message, I'm sure the thing I'm receiving is an entire message. Which again is the natural thing to do. But as we will see, TCP doesn't do the natural thing. In principle, UDP is doing the best it can on a network that is most of the time reliable, but not always. This means that sometimes messages may be lost. We have seen reasons for dropping packets. It can be a bit error somewhere on the medium, and you send it over Wi-Fi, then there is an uncaught shadowing that creates unexpected bad signal-to-noise ratio. It can be also overflow in bridges or routers. If you have a queue at an output port and for some reason the output port is too busy, then the packets are dropped and then it's lost. In principle, packets arrive in the order they were sent, but there's no guarantee that it will always be the case. IP tries hard to do it, but there's no guarantee of that. And UDP doesn't care, because UDP treats every packet, every datagram more exactly, as a single unit, and there's no attempt to reorder them if one is coming earlier than expected. A UDP message, I mentioned a packet or datagram. The correct term is datagram. A UDP packet can be larger than the maximum size for the IP layer. The maximum size for the IP layer is, in principle, the maximum size for the MAC layer minus the IP header. So the MAC layer is 1,500 bytes. So the IP packet has, if it's IPv4, 20 bytes of header. So the maximum message size that we can send in one packet is 480 if we use IPv4, and 460 if we use IPv6. And that should include the 8 byte of UDP header. UDP allows messages to be larger than a single IP packet. So if that happens, UDP will do what is called fragmentation. Fragmentation is in fact done at the IP layer. We'll talk about it in a few more hours. So a UDP message can be much larger than an IP packet, not infinitely large. I mean, most applications require that. The most operating systems require 64K. And this fragmentation, if it occurs, is hidden by UDP. So if a UDP application sends a message of 2,000 bytes, it will be broken into two IP packets by the IP layer, in fact. The two IP packets will be reassembled at the destination if none of them is lost. And then they will be made visible to the socket as one message. And in principle, there's no way to read part of the message, the first packet or the second. When you will do a call to the socket layer, it will say the message has arrived or not. If no message has arrived, you can read nothing. And the operating system will consider that no message has arrived if, for example, only the first packet has arrived. If the datagram was broken into two, the first one arrives and the second is lost, then the IP layer will consider that the entire message is lost. This is how fragmentation works, and it is consistent with the concept that it's message-oriented. So the goal of UDP is to simply give entire messages. You will see in the lab, when we read data, it has an implication. For example, if I have a streaming application that sends a sequence of packets, for example, a sensor that measures things every 100 milliseconds and sends new data every 100 milliseconds, if there are delays on the network for whatever reason, some of those packets may arrive together. If you use TCP, they may be glued together. If you use UDP, even if they arrive together, it will be visible at the interface that we have two, for example, messages. So if you do a read twice, you will get two messages. If you use TCP and you do a read, then there's no way to know whether the 200 or 2,000 bytes that you're receiving come from two different packets or not. You will need the application logic to take care of that. That's what it means. This is typically how we use UDP. If we use lower level, like we will do in Lab 3, I have a client and a server. A server is by definition a program that's waiting and listening for things to happen. A client, in contrast, is working on demand. When a client has nothing to do, it does nothing, whereas a server is always up and running. That's the true definition of a server. Very often a server means a machine that is in the back end somewhere, but that's the true definition. So assume you have an application that sends one message to somebody who's listening to it. So the guy who listens has to be listening before, and the simplest way to listen is to, so socket means create a socket. That's instruction to the operating system to create a buffer in which to place the messages that will arrive. Bind simply means gives instruction about the port number. If this is a server, for example, if you're a DNS server, in the bind you will say, bind me to port number 53. That means give all the data that arrive to this machine to port 53, give them to me, to this socket. Packets that arrive to another port number, I don't want to see. In the bind, you can do lots of other things. You can also, if a machine has several IP interfaces, IP addresses, you can decide which of the IP addresses should send things to here. And then, once this has succeeded, all of those are system calls, so they may fail if there's not enough resources, for example. If they succeed, then you can start doing useful work, and for a server, for example, it may consist in doing a receive from. Receive from means receive. Receive is the same as read. If this would be a file instead of a socket, that would be read, some data. But the UDP read is has an implicit concept of read the entire message, whatever the message is. And receive from means not only will receive a message, so when this will return, depending on the operating system, a pointer or a buffer that contains the message, but it will also contain another information, which is the source IP address and source UDP port number. Because a server, a priori, can receive data from anyone else, from anyone. If this is a DNS server, you can get it from anyone. And this from indicates that we will give the information about the source that will typically be used for sending a response. For example, if this is a DNS server, it will look up its database to find the answer to the question that's asked in the message, and then it will respond to the source by looking at the source IP address and source port number that it has got from this call here. Here there is a dotted line, which means that by default, if there is nothing to receive from, which happens when you boot the server and nobody has yet started the application on the client side, the call will typically block. That means this program is stopped until there is something in the buffer. When there is something in the buffer, the execution of the program will resume from this point here. You can control with options whether this is blocking or not blocking, but the default in principle is to be blocking. And the client side will be similar, except the client will do a send to. Here it means by this socket we can send to multiple destinations, and send to means I have to give the message I'm sending, plus also the IP destination address and the port number. We say here that UDP is a non-connected protocol. Non-connected means there is no connection between the two ends. Connection means a synchronization, state information that they share. Here there is none, which means you can start the client and without knowing anything of what the server has done, you can send the data and it will work if a server is up and running. If nobody is listening, of course, the data will be sent and lost. If there is a server listening to that port, the data will be received. But the only information you need is the port number, and not what the state of the server is. You can, what is called, connect UDP sockets by caching the information about the other end. For example, if this client is always sending to the same server, and the server is always receiving from the same client, then you can add another call, which is a connect call, that has the effect of caching the destination IP address and the destination port number. And if you have done this connect call, which means you have stored in a cache information about the other end, then you do a send simply and not a sends to. Similarly, if you have connected this one by caching information on the other end, you will do a receive, and that means this socket can be used only to receive UDP messages from one specific source. This is the concept of a connection for UDP. For TCP, we will see there's a concept of a TCP connection, but it's a much stronger concept. In a TCP connection means there's a lot of state information that needs to be synchronized. Here it is simply caching information to shorten those calls here. Is there a UDP v6 and a UDP v4? The good news is no, there is not. UDP is a transport layer protocol. It's the same whether we use IPv4 or IPv6. So we've seen before that the MAC is the same whether we use IPv4 or IPv6. We don't need to change the switches, with the notable exception of multicast. Here is the same. The layers above the network layer are not modified. So UDP is exactly the same. The header is the same. Except, of course, the programs are not the same. So when in the lab, we will do a program that uses UDP sockets. If it uses UDP sockets with IPv6 or with IPv4, it will typically be different system calls. Because, for example, if you use UDP with IPv4, you need to pass information in the send to, which is a remote IP address. The remote IP address has to be an IPv4 address. If it's an IPv6, it won't work. We will see also there are, in Python that we recommend to use for the labs, there are sockets that are able to use both v4 and v6 addresses. An application program, in principle, if it connects, for example, to a DNS server, it needs to know whether the DNS server will be working with IPv4 or IPv6 or both. And the way this is typically handled is by DNS. So if I go to a DNS server called, for example, dns.epfl.ch, I go to the DNS to find the IP address. Then if the DNS returns to me only an IPv4 address and no IPv6 address, it means this DNS server works only with IPv4. So I have to connect to it using IPv4. If it returns both an IPv4 and IPv6 address, I have the choice. So it will be up to the local policy of this machine to decide what to do. Many machines prefer IPv6, but some machines prefer IPv4. It will be based on the local policy. In principle, we prefer IPv6, but we do lots of bad experiences with IPv6, like we do in the lab. So in principle, so this principle is not always followed. It's important to reason correctly about sockets, to have a mental model of how the operating system views sockets. It's not necessary. You can do a program that will work without having this mental model, but having the mental model will help avoiding mistakes and understanding what is happening, in particular when things go wrong. It's when things go wrong that you need the correct mental model. So this is the how an operating system handles sockets. So you have an application program that uses socket calls, and if it uses UDP sockets, the data that arrive to this program are stored in a buffer, which is shown here. And it's only when the application program does a read call that the data is removed from the buffer. By default, as soon as one application program does a read call on one socket, the data that is read is destroyed, removed from the socket. By default, as usual, with socket option, you can decide to change this default and keep the data even though you've read it. But if you do that, very soon you will have a problem that the buffer will be full and probably won't work long. When packets arrive to the machine, they are tagged as IPv4 or IPv6 packets. We know how. The MAC layer header will tell us whether it's an IPv4 or an IPv6 packet. So they are forwarded inside the operating system to the IPv4 network layer or the IPv6, which are two distinct entities. And then all the packets that go to a given address, in the simplest case, there's only one IPv4 and one IPv6 address to those machines, are sent to the sockets, and they are demultiplexed using the different port numbers. Here I'm showing two different port numbers. So different port numbers means different receiving buffers, and the data are sent to the different buffers. If there is an IPv6 packet, the same happens, but they are really treated as different spaces. In particular, if the packet has arrived over IPv6 to a given port number, it's put in a different buffer than if it has arrived to the same port number over IPv4. So in some sense, there is not a UDP for IPv6, but there is a different socket for each IP address. And if you have two different IP addresses on the same port numbers, you have two different sockets. In particular, if you have an IPv6 address and an IPv4, they are different addresses, and they are different sockets. A socket, the main part of a socket, is, in this case, is the receiving buffer. The receiving buffer is necessary because when the data arrives, we have no guarantee whether the application is ready to read it. Even if it's ready to read it, things are probably not synchronous, so the data probably arrives a bit before the application reads it. Worse, it can be that the application program is very busy. If you have a very busy DNS server that's handling millions of requests, perhaps some of the requests come faster than the application program is able to handle them. If that happens consistently, there will be problems somewhere. If you have a slow application program and lots of data that's arriving on a very fast network, what will happen? Yes? Some packet will be lost. So the packet arrives, the buffer is full here, so some packet will be dropped. Now, what will be dropped is hard to guess exactly, and many operating systems do lots of very sophisticated optimization procedures, but this buffer has a finite space, and certainly something will be dropped. Perhaps it's the arriving packet that is dropped, or it's the older packet in the socket that will be dropped, depending on the replacement policy for this buffer. But some data will be lost if that happens. The data will be lost like they can be lost in bridge buffer or in router buffer. Now, it's a bit a stupid loss. You don't like to lose things at destination. That's the worst place to lose data because the network has worked to carry the data and you lose them at the destination. But the only way to avoid this is to perform what we call flow control, is to guarantee that the application program is, or that the sources are not sending faster than the speed at which the application program can receive them. If one way to do it, if you're a DNS server, for example, is to make sure you have a very, very fast application program that's able to handle packets as fast as they can arrive, limited by the speed of the network. If you have a very complicated server that does a lot of jobs, if receiving a single packet requires a lot of work here, for example, because you have to access a database, do an authentication, do a payment, do that kind of things, then you need to manage at the application layer the flow control. And typically this is done by using TCP. So TCP will manage in some sense the speed at which the data is arriving. UDP does not do it. A quick question. Okay, so my pickup application hangs on the, because it's installing a new version. So we'll do it here manually. Who says A? So we lose anonymity. Okay. Who says B? Oh, come on, be courageous. Okay. Who says C? Okay, well, of course, you are right. The correct answer is A. Which means that if you're writing a UDP application, you need to take care of the retransmissions. So you send a query to a DNS server. Well, you don't need to do it yourself if it's the DNS resolver. But when you will do the applications in the labs, you will need to manage it. So those who wrote the DNS resolver had to take care of that. So you send a query, then you need to know whether the query has been received. So one way would be to require an acknowledgement, like we've seen in the stop-and-go protocol. But because DNS queries are supposed to be small things that are processed fast, it's easier to simply wait for an answer. When you send something to a DNS server, normally it responds. Perhaps it responds with the correct answer, or it responds with a redirection asking you to go and see somewhere else. So you expect a quick response. If no response comes, then you treat that as an absence of acknowledgement and you send again. Of course, while sending again, you may want to do a bit of flow control. You don't want to resend and then if nothing comes, send again and again. You want to slow down the rate at which you're receiving. So the timer you use to wait until you have received an answer and to repeat will increase. If I send a message, I wait for some time, a few seconds. After a few seconds, if no answer comes, I try again, but I wait for a longer time if I'm sending to the same server in order to avoid flooding the server. Voilà, this is how UDP works, and it's very simple, so that's all I will say about it. TCP is a bit more complicated. As we have seen, TCP solves the problem of packet losses. It doesn't mean that TCP guarantees that there's no loss. It just guarantees that everything that anybody could do to repair the losses has been done already. But if you're talking to the server and the server crashes and does not respond, then TCP will not be able to create an answer for you. Or if you connect to a server over a wired Ethernet and somebody comes and cuts the wires, TCP will not be able to repair the wires for you. So it will never guarantee that everything works. But if something can be done, it will be done, and you cannot do better than TCP. So there's no point trying to retransmit once you use TCP. While doing that, TCP adds, or does it in its own way. Not only it offers a service, what we call a reliable service, which means it does everything that can be done to repair data losses, but also it guarantees in sequence, which is, I would say, very specific to TCP. In sequence means that if the source has created a number of data, 1, 2, 3, 4, if number 3 is lost, then at the destination we will receive 1, 2, 3, 4, 5, which means at the destination perhaps the operating system has received 1, 2, 4, 5, but 3 is missing. If the application does a call to TCP to read the data, it can read 1, it can read 2, but that's all. It will not be able to read 4 and 5 because TCP must deliver things in order. It cannot deliver 4 because 3 has not yet been received. So it will hide away from the application data that is perhaps already received but is not in sequence. Other protocols like STCP or WebSocket are able to transport entire messages reliably and do not have this requirement. Here, this is what TCP does. So the reason for that is TCP is simulating a physical connection. If I have a wire between A and B, I have two PCs that are connected by Ethernet on a wire, a single wire with no switch in between. Losses on these wires will be extremely rare events. You might work for days without a single packet loss. And packets will always be transferred in sequence. They can overtake each other on the wire. So TCP is simulating that. When A is connected to B, it is as if I had a virtual wire between A and B that delivers the data exactly in sequence. It's not exactly like a virtual wire, of course. There will be a difference. Where will the difference be? In delay, exactly. Because if packet number 3 is lost, it will take some time for TCP to repair the losses. We'll see that TCP uses repetition it will retransmit the missing thing, but this will take some time. So we will receive 1, 2, then nothing for a long period of time, then 3, 4, 5. Whereas on the physical wire, of course, the data would have a very predictable and deterministic delay. So delay is the difference. TCP does a wire emulation but does not care very much about delay. TCP is not meant to provide a low delay service. If you need a low delay service, you can use TCP, but it's not guaranteed that you will always have low delay. If you really must have low delay, you have to use UDP and then manage reliability with your own way. So, how does TCP achieve its goal? Well, it does the simplest way that we can think of, perhaps. It numbers all the data, and it makes sure when we start the data, the two ends agree on what is the beginning of the numbering. In the simplest case, we could imagine we start at 0, but TCP doesn't do that for various reasons. And that's called synchronization of the sequence number. And then once the data is numbered, it's very easy. When you receive data, you look for contiguous numbers. And if you see a gap, then you know something is missing, and you ask for a retransmission. Okay, this little music signals the end of the course for today. So that's all for today. Thank you very much for your attention, and see you tomorrow for the quiz.